Howdy there, Mr. Sutton here, bringing you the AB Calculus 4-4 Extra Practice Number 1 solutions on concavity. On this problem, I want to determine the intervals where the graph of this thing is concave up and concave down. So for that, I need to look at the sign of f double prime. Well, let me take f prime first. That'll be 3x squared plus 16x plus 16. And let me just go one more prime now, f double prime. That's going to be 6x plus 16. I need critical values for this, so let me set this equal to 0. And I can solve this pretty quickly if I subtract 16 and divide by 6. Negative 16 over 6 reduces to negative 8 over 3. So that's my critical value that I'm going to put on an f double prime number line here. And now I can test around that critical value. Let me plug in something less than negative 8 over 3. How about negative 9 over 3, aka negative 3? If I plug that into f double prime, that's going to be negative 18 plus 16, which is negative. Something bigger than negative 8 over 3, I mean, why be too creative here? I'll just use 0. So that's 0 plus 16, which is positive. Now I notice that f double prime is positive from negative 8 over 3 onwards. Therefore, f is concave up from negative 8/3 to positive infinity. And since we're negative for f double prime going the other direction, f is going to be concave down from negative infinity to negative 8 over 3. On this problem, I'm trying to figure out where the graph of this function is concave up and down. So for that, I need the second derivative. First derivative, we're going to have the, 2/3 times a negative 1, so negative 2/3 times an inner derivative of 7 here. So negative 14/3 when all is said and done, times all of this stuff to the negative 1/3 if we subtract 3/3. The second derivative, I've got negative 14/3 times negative 1/3. That's 14/9. But we have to multiply by the inner tail here of 7. So that's going to be 98/9. All of this stuff to the negative 4/3 power. I'm going to turn this into fractional exponent form now, or actually it's already a fractional exponent. Let me make this fraction and radical form, so I'm not trying so hard to find critical values with this thing. So this is going to be the cube root of 7x plus 14 to the 4th power, and all that's going to be in the denominator next to the 9. There we go. Now, because this is a fraction with a constant numerator that's not 0, there's no way this fraction can ever equal 0 by itself. So if you're looking for those critical values, they don't exist. However, there are other critical values where the derivative itself does not exist. So for example, with this variable down here, if you plug in negative 2 for x, you're going to zero out the denominator. So we know that f double prime does not exist at x equals negative 2. So now that gives us at least one critical value we might conceivably do some sign analysis around. The trouble here is, you've got a positive numerator. It's always positive. Down here, since you're raising the stuff in here to the 4th power, it comes out positive, and there's nothing else down here to reverse that. So this whole thing is always going to come out positive as long as you're not plugging in negative 2 where it's undefined. Since it's positive pretty much everywhere except negative 2, we can say that f is concave up from negative infinity to negative 2 and negative 2 to positive infinity. And it's going to be concave down, well, nowhere, because it's either undefined or positive everywhere. On this problem, we're given that f is a function defined for all real numbers. We want to know what condition assures it has an inverse function. So what does that mean anyway? Well, inverse function is a function that takes the output and gives you back the input. And one of the ways that we test for something having an inverse function or not is something called the horizontal line test. If you pass the horizontal line test, which I'll call HLT for short, you have an inverse. So what does it mean to pass the horizontal line test anyway? Well, it means that it's impossible to draw a horizontal line that touches your function more than once. And the reason that this guarantees you have an inverse is because, let's say that you did draw a horizontal line and you're touching more than once. That means you have two different points on the graph that are at the same height, two different y values same y value for two different x values. If you have two different inputs giving you the same output, that means when you reverse this thing and take the inverse, you're going to have an input giving you two outputs, and the inverse function is going to fail the horizontal line test. So long story short, if we can draw a horizontal line that touches in more than one place, it's going to fail the horizontal line test and not have an inverse. All right, looking at our different options here. Option A, function f is periodic. Well, they're talking about functions like sine and cosine. So obviously you can touch them multiple times with a single horizontal line. Sine of x, for example, is going to fail the horizontal line test. So choice A is not the answer we want. How about the graph of f is symmetric with respect to the y-axis? So for the rest of these, we're just going to find counterexamples that mess things up here. So symmetric with respect to the y-axis, well, how about the line y, or the curve y equals x squared, a parabola? That is going to fail the horizontal line test. And if you look at some of these other options, concave up, well, hey, x squared is concave up, fails the horizontal line test. Continuous, x squared is continuous, fails the horizontal line test. You can actually use x squared to disqualify choices B, C, and E, and I'm sure there's other functions too, but that's just kind of an easy one that comes to mind. So that leaves us with choice D. By process of elimination, it has to be the answer. But why does this guarantee that we have an inverse? Well, strictly, so this choice B, C, and E were no's, but now strictly increasing for choice D, that basically means you're not going to hit the same y value twice. If you are just going up and up and up and up forever without pause, that means you never come back down and hit the same y value again. So this will guarantee that we have an inverse. It'll guarantee we pass the horizontal line test. So then choice D is what we're looking for. On this problem, g is a twice differentiable function such that g prime is greater than 0 and g double prime is also positive. And we're told that g of 4 is 12, g of 5 is 18. So which is a possible value for g of 6? The key here is g prime is positive, so we know we're increasing. G double prime being positive means that we're increasing the rate of increase. So we are, to sum it up, increasing at an increasing rate. So we should end up with a number for g of 6 that is higher than we started with, and higher by more than g of 5 was higher than g of 4. So to write it down, on 4 to 5, we had a rate of change of from 12 to 18 was 6. We increased by 6. This means since we're increasing at an increasing rate, basically going up and speeding up the rate of increase, on 5 to 6, between our last known point and the one that we're trying to predict, g should increase by more than the last increase. It should increase, and it should increase by more than 6. So taking a look then, from 18, 6 more than 18 would be 24. So g of 6 needs to be more than 18 plus 6, more than 24. The only answer choice that's actually more than 24 is 27, choice E. On this problem, f is a function such that f equals x cubed minus 6x squared. We want to know when this thing's concave up, which is to say we want to know when f double prime is positive. So let's go ahead and take a couple derivatives. F prime will be 3x squared minus 12x, and then f double prime is going to be 6x minus 12. So let's solve for some critical values here. Set it equal to 0 and solve. So we see that this is going to be true when x is 2, if you add 12 and divide by 6. So let me make an f double prime number line with a 2 as a critical value. Testing something to the left here, doing a little sign analysis, let's plug in 0. So if I plug that into f double prime here, that's basically 0 minus 12, which is negative. Something bigger than 2, how about 3? That would be 18 minus 12 if I plug it in, so that would be a positive. We want concave up. That's going to be where f double prime is positive. So we see here that we are concave up for x greater than 2. And that's going to be choice A. For this problem, we're given this table of function values for f, and we want to make some speculations about f prime as to whether it's positive or negative and increasing or decreasing. Well, we can't really figure out what f prime is everywhere between 1 and 5, but we can at least use the average rates of change on each of these subintervals here to make some speculations about f prime. They said it's twice differentiable, and you'll learn later on that that means that there's a value of f prime somewhere on each interval that matches the average rate of change. Anywho, Let's look at these decreases here. From 9 to 4, that's a decrease of 5. And then from 4 to 0, we're going down 4. From 0 to negative 3, we have an average rate of change there of negative 3, and then negative 2 is the next one. So conclusions we can draw from this. First off, the original function is decreasing. It's going down. This means that f prime has to be negative, at least somewhere on there. If it's positive, that's kind of suspicious for these things to be going down. And notice it says negative for the whole interval 1 through 5. Positive for the whole interval 1 through 5. I mean, we could argue that maybe f prime turns positive somewhere kind of off camera, but we can't claim it's positive for this whole interval if these f values are going down. Okay, so we've got that established. We're really picking between answer choices A and B. It's all about whether f prime is increasing or decreasing. So one other thing we notice, the rate of decrease, negative 5, negative 4, negative 3, is becoming less negative. Well, if the rate of change of something is becoming less negative, that means technically it's increasing. If you're getting closer, if you're in negative territory and you're getting closer to the x-axis, you're going up, you're increasing. So we can see then that this rate of change, which we call f prime, is increasing. That means we're going to have to pick answer choice B. For this problem, we're given this function and we want to know where the graph of f is concave up. Now here's where you have to be really careful, because normally they give you f and you have to take 2 derivatives to get the second derivative and do sign analysis. But look what they gave you here. This is f double prime. They already gave you the thing that you need to do sign analysis on. So you just need to find critical values for this and do your sign analysis. Setting this equal to 0 then, we see that we have critical values at x equals 0, and for this parentheses, x equals negative 2. Sign analysis time. This is an f double prime line. We've got negative 2 and 0 as our critical values. Testing out something to the left of negative 2, let me use negative 3. Plugging that in my second derivative, which they handed to me on a silver platter here, we have a negative out here. This squared term is always going to be positive, so it's really just this x here that determines the sign. So plug in negative 3, the whole thing's negative. Something between negative 2 and 0, like negative 1, plug that in. Again, the only thing that matters is this x out in front, so the whole thing is still negative. Something bigger than 0, like 1, well, now that makes everything positive. We wanted concave up, so that's going to be wherever f double prime is positive. Here, that's going to be for x greater than 0, so that's choice B. On this problem, for x greater than 0, which is important that they specified that, we're told f is a function whose first derivative is ln of x over x, and the second derivative is 1 minus ln of x over x squared. We could have found the second derivative, but it was nice of them to just give it to us. So we want to know which of the following is true. So we have a bunch of statements talking about whether f is decreasing or increasing for x greater than 1 and on this other interval, and also talking about the concavity. So we're going to do a little bit of sign analysis around critical values for both f prime and f double prime and see which one of these we need to pick. Let me start with f prime. So I'll find some critical values by setting this equal to 0. And if I do that, the only thing that really matters is the numerator equaling 0. ln of x is going to equal 0 if I raise e to the both sides here. E to the 0 is going to be 1. Or you could think ln of 1 equals 0. Either way, that's our critical value. We also know that f prime does not exist for x equals 0 because of the denominator, and also really for any negative values because you can't ln a negative number. You can't log a negative or 0. So this is undefined for x less than or equal to 0. But they spelled out x greater than 0 in the beginning anyway, so that's kind of neither here nor there. So sign analysis starting at 0 around x equals 1, and this is f prime now. Plugging in a number less than 1 but also greater than 0, that's important here. Well, what would that be? That's easy to take the ln of, because this was a no calculator problem. Well, how about e to the negative 1? It's 1 over e, right? And e is bigger than 1. So that's going to be a number that's between 0 and 1. And it's also something that's pretty easy, no pun intended, to take the ln of. So if you take the ln of e to the negative 1, ln of e to the negative 1 is just 1, or actually negative 1 rather. So you have negative 1 over a positive number. which is going to come out to a negative. And now something bigger than 1, well, e is the one that comes to mind. ln of e is just 1 over a positive gives us a positive. So we see that this function is decreasing from 0 to 1 because f prime is negative, and increasing from 1 to infinity. So that ought to help us narrow down some of the answer choices. For example, if you're increasing from 1 to infinity, that means you're most likely dealing with answer choices C or D. A and B, they have the decreasing happening in the wrong place. And honestly, F or E also has the wrong kind of increasing because 1 is, they're saying we're increasing somewhere we're not. We're only increasing after we get to 1. So to pick between choices C and D, we need to talk about the concavity. Let's take f double prime and find some critical values there. So setting that equal to 0, 1 minus ln of x equals 0. This is going to happen if you, add ln to the other side and e both sides. This is going to be x equals e. If you take the ln of e, that's 1. 1 minus 1 is 0. That's another way to think about it. And now, just like before, you can't plug zeros or negatives into the ln function here. So this derivative, this is a second derivative now. This second derivative is also going to be undefined for x less than or equal to 0. So here's my number line. This is an f double prime line now, starting at 0. And now our critical value is e, which makes sense. If you look at the answer choices, they're all talking about concavity with e. So you probably could have figured that out even if you didn't do all this work. So now let's do a number between 0 and e. Well, this is an easy one. 1, literally. If I take the ln of 1, that's just 0. So 1 minus that gives me a positive. And then I have a positive downstairs, always with the x squared. So that's positive overall. What's bigger than e that's easy to plug into ln? Well, how about e squared? So ln of e squared is 2. 1 minus 2 is negative over a positive, gives us a negative. So this is saying we are concave up from 0 to e and concave down from e to infinity. So we were choosing between answer choices C and D. And the one that says we are, C says we're concave down greater than E. That's what this says here. So C looks good. D says we're concave up for x greater than E. That's not true. We're only concave up between 0 and E. So choice C then is the one that matches what we have here.